This is just going to be a quick recap of how to carry out a number of simple titrations calculations. The method will be shown on the left-hand side of all of the slides for reference. So, when we're carrying out titrations, we always have one of the two reactants which we have known information for, enough to actually calculate the number of moles. Knowing the number of moles of this reactant allows us, by a use of the balanced equation, to find the number of moles of the other reactant and hence either its concentration or volume, depending on what is asked for. So, how to carry out titration calculations? We'll be always given information on the volume and concentration of the reactants, though we will be missing either the volume or the concentration of one. So with our example, we are given 25 centimeters cubed of 0.2 mole per decimeter cubed sodium hydroxide, which is titrated against sulfuric acid, H2SO4. 14.3 centimeters cubed of H2SO4 is used. Calculate the concentration of the H2SO4 in moles per decimeter cubed. And there, as we should usually be given, is the balanced equation, which will be important for determining the ratio of the moles. So the very first thing that we want to do for this type of question is to lay out a table with the balanced equation on the top and then rows for the volume, concentration and moles of the relevant chemicals. So this is the table as I would construct it. You can see that I've blanked out the boxes for the two products because the question doesn't actually ask us about the products. We're only asked about the two reactants. So we don't need to give space for those products. Step number 2, we then want to fill in the known volumes and concentrations and mark whichever value we are supposed to calculate with an asterisk. So we are told we have 25 centimeters cubed of sodium hydroxide, we have 14.3 centimeters cubed of sulfuric acid, and we are told the concentration of the sodium hydroxide is 0.2 mole per decimeter cubed. We are asked to calculate the concentration of the H2SO4, so I'm going to put an asterisk in that box to remind me that that is what I am working towards calculating. Step 3, we then want to divide our volumes by 1,000 to convert from centimeters cubed to decimeters cubed. This is actually very important because the equation for calculating concentrations and moles always uses volume in decimeters cubed. So you can see I've got the formula triangle up there to remind me. Okay. So 25 divided by 1,000 gives us 0.025 and 14.3 divided by 1,000 gives me 0.0143. One thing here, this is a relatively easy calculation to do. You are simply moving the decimal place 3 spaces to the left. This is not something that you should need a calculator for. Step 4, we are then going to use the equation moles equals volume times concentration to find the number of moles of our known reactant. Now here, it's the sodium hydroxide that we have both the volume and the concentration for, so that's the one we're going to calculate the moles for. And just a reminder, if you are using the formula triangle, you can find the calculation that you need to do by covering up the relevant parts. So in this case, if I cover up moles, I can see that I've got concentration times volume is how I find that. So the moles of sodium hydroxide is going to be 0.025 times by 0.2, which gives me 0.005 moles. Note here that I have used the volume in decimeters cubed as I calculated in the previous step. For Step 5, you then want to apply the reacting ratio from the equation to the known moles that we've just calculated to find the moles of the second reactant. So if I go to my equation, I can see that I've got a 2 to 1 ratio, 2 NaOH to 1 H2SO4. So I've got to apply that by dividing my number of moles by 2. So 0.005 divided by 2, which gives me 0.0025 moles of H2SO4. Then 6, we're going to use the formula triangle to find the unknown value. So this is our box which we've put our asterisk into. We need to remember if we've got a volume to convert decimeters cubed back to centimeters cubed if asked. Now in this case we're calculating a concentration, so we don't need to worry about that. So I'm going to be calculating concentration. So if I cover up concentration in my formula triangle, I can see that I calculate that by using moles divided by volume. And remember, of course, that the units of concentration actually tell you that's how you should calculate it, moles divided by decimeters cubed. So our calculation here is 0.0025 divided by 0.0143, which gives us 0.175. So I can then say that the H2SO4 is of 0.175 moles per decimeter cubed concentration. One thing to note with these kind of calculations, when you are rounding any of your numbers, so if you have a long decimal in your calculator and you do need to round it right down, make sure that you are using 3 significant figures as the minimum number of significant figures. So I've given there some examples of how to appropriately round to 3 significant figures when you've got numbers that look a little bit different there. In this case, the only place where I really needed to do any rounding was on that final calculation, and so I've given it appropriately to 3 significant figures. Right, let's have a look at a couple of additional examples then. So, example 2, we've got 15 centimeters cubed of 0.55 mole per decimeter cubed HCl titrated against KOH, potassium hydroxide. 21.7 centimeters cubed of potassium hydroxide is used. Calculate the concentration of potassium hydroxide in moles per decimeter cubed. So, first step, lay out our table. Okay, so once again, we've got the balanced equation on the top to provide us with our reacting ratios. And once again, because we're not interested in the products of this reaction, we have blanked out those last 2 columns. We've not made them particularly large because we're not going to be using them. Step 2, fill in our known volumes and concentrations and mark the values to be calculated with an asterisk. So here we've got 15 centimeters cubed of HCl. Make sure that you put that in the right box. The HCl is second in the equation, but it's the first thing mentioned in the question. So make sure that we're getting that value in the right place. The KOH, we've got 21.7 centimeters cubed. And we're given the concentration of the HCl as 0.55 as well. The asterisk is going for the concentration of the KOH, which is what we are asked to calculate. Calculate the concentration of the KOH in moles per decimeter cubed. Step 3, divide the volumes by 1,000 to convert from centimeters cubed to decimeters cubed. So 15 divided by 1,000 gives us 0.015 decimeters cubed, and 21.7 divided by 1,000 gives us 0.0217 decimeters cubed. We're then going to find our number of moles for the reactant, which we have 2 bits of information for. So in this case, the HCl, we know both the volume and the concentration, so we can go on to find the moles by multiplying those 2 together. So 0.015 times by 0.55 gives us 0.00825 moles. We then want to apply our reacting ratio. Now in this case, we've got 1 KOH plus 1 HCl, so that's a 1-to-1 ratio. So I don't actually have to do anything here. I just transfer in the same number. 0.00825 moles of HCl will react with 0.00825 moles of KOH. Then the last step, use the formula triangle to find the unknown value. Now, once again, I'm finding a concentration, so I cover up the concentration part of my formula triangle, and I can see I need to do moles divided by the volume in decimeters cubed. So in this case, 0.00825 divided by 0.0217, giving us 0.380 moles per decimeter cubed, which is my final answer. So KOH is of a 0.380 mole per decimeter cube concentration. Note here as well, I am giving my final answer to 3 significant figures. It just happens that the third significant figure in this case was a 0. Okay, so I should still include that to make it clear that my answer is to 3 significant figures. Right, okay, so the last example that we're going to have a look at is a little bit different. Example 3. 10 centimeters cubed of 0.15 mole per decimeter cubed phosphoric acid, H3PO4, is titrated against NaOH of concentration 0.5 moles per decimeter cubed. Calculate the volume of NaOH needed in centimeters cubed. We've again got our balanced equation underneath. Now, the thing that's different in this case is that unlike the previous examples, we know the concentration of both reactants, but we do not know the volume of the sodium hydroxide, and this is what we are trying to find out this time round. So we lay out the table just as before, and once again, the columns for the products can be blanked out and left quite small because we are not going to be filling those in. Let's then put in the values that we know. So we've got 10 centimeters cubed of phosphoric acid, and we have a concentration of 0.15 moles per decimeter cubed of phosphoric acid. And then for the NaOH, we are told that that has a concentration of 0.5 moles per decimeter cubed. So we got all of those values from the question filled in into the correct boxes. Our asterisk in this case, though, is going onto the volume line for the sodium hydroxide because we are asked to find the volume. Step 3, just as before, we need to convert any volumes into decimeters cubed. We only have to do this once in this case. So 10 divided by 1,000 gives us 0.01 decimeters cubed. And then just as before, we are going to find the moles by multiplying that volume and concentration. So H3PO4 is the one that we have both the volume and concentration for. We're going to multiply that volume by that concentration. So 0.01 times 0.15 giving us 0.0015 moles of that. Now, step 5, apply the reacting ratio from the equation. This is an interesting reacting ratio. Here we've got a 1:3 ratio. So we need to multiply our moles of phosphoric acid by 3 to give us our moles of sodium hydroxide. So 0.0015 multiplied by 3 gives us 0.0045 moles of sodium hydroxide. Now for step 6, we're going to use our formula triangle to find the unknown value. Now in this case, unlike in the previous ones, we're finding a volume. So if we go up to our formula triangle and cover up the volume corner, we can see that the way to calculate this is by using moles divided by concentration, and this is actually going to give us our volume in decimeters cubed, which we'll have to deal with afterwards. So moles divided by concentration will give us 0.0045 divided by 0.5, which gives us 0.009 decimeters cubed. And note here, because we are using this formula triangle, we are getting the volume initially in decimeters cubed. Now the question asks us what is needed in centimeters cubed. So we have to do a reverse conversion, timesing our number of decimeters cubed by 1,000 converted into centimeters cubed. So that will give us 9 centimeters cubed. So our final answer is to say that 9 centimeters cubed of sodium hydroxide of the given concentration is going to be needed.